Question 1. Define electric field strength at a point in an electric field, and this is worth 2 marks. Electric field strength is defined as the force per unit, and this is quite important, positive test charge. Why is it important to write the word positive for the test charge? Well, the direction of the electric field is dictated by the direction that a positive test charge would take. So if you're looking at a positive charge and you were to draw the electric field surrounding that, then a positive test charge placed here would be repelled from that positive charge, which tells us that the direction of the electric field is radially outwards. If, however, we're looking at a negative test charge, then the charge would be attracted towards, because it's positive, this positive test charge, would be attracted towards that negative charge. So the field is radially inwards. If we're looking at a uniform field, let's look at one here, and we have positive plates up here and negative plates down here. Our electric field would be uniform, with edge effects, of course, and the direction the electric field would take would be the direction that a positive test charge would take at any one point. So it's from positive to negative. So that's why it's important to get those 2 marks. We have to write the force per unit positive test charge. B. 6-point charges of equal magnitude Q are held at the corners of a hexagon with the signs of the charges as shown. Each side of the hexagon has a length A. P is at the centre of the hexagon. Show, using Coulomb's law, that the magnitude of the electric field strength at point P due to one of the charges is. In the first question, we were asked to define the electric field strength, and we said that the electric field strength is the force per unit test charge. And that's how you write it using an equation. We know that Coulomb's law is the force between 2 charges, which is this. So we're going to pop this in to here. K, Q, Q, over Q, R squared. These 2 test charges cancel. So we're left with the electric field strength is equal to KQ over R squared. Now in this case, I was using R. They're looking at A. A is the distance between the 2 charges here. If we were to think about a hexagon is made up of equilateral triangles. And that is triangles that all have the same length of side. That means that this side of the triangle is A and this side of the triangle is A, which means the distance between the charges and this point P in the middle at all points is A. I'm going to rub that out just now because I need to keep it clean for the next question, but bear in mind that the distance between the charges and point P is A. I feel like we're going to use that later. 2. On the diagram, draw arrows to represent the direction of the field at P due to point charge A, label this direction A, and point charge B, label this direction B. If we go to point P, that's where our positive test charge would be. So we imagine that's a positive test charge. We can see that A is a positive charge. That means that this positive test charge would be repelled from A, meaning it would be going in that direction, and we're going to label that A. Conversely, B is a negative test charge, and our positive test charge at P would be attracted towards B. That means it would be going in that direction for B. One thing to note is that I've made them both the same size, and the reason I made them both the same size is because they'll be experiencing the same magnitude of force per unit charge based on the fact that everything is the same distance apart. So these 2 arrows have to be the same size. 3. The magnitude of Q is 3.2 microcoulombs and length A is 0.15 metres. Determine the magnitude and the direction of the electric field strength at point P due to all 6 charges. I think we're going to have to draw some more arrows. We've already drawn our electric field strength due to point A. Let's look at the electric field strength due to this charge here. We know that the positive test charge will be attracted towards there, so we'll have an electric field strength in that direction. Now we'll look at this positive charge. The positive test charge will be repelled, and it will repelled away from there in that direction. Now we'll look here. We know that this is negative. We're looking at a positive test charge, so it's going to be attracted towards it. We've already done B. We've circled that already. Let's look at this one. P will be repelled from that positive charge, and it'll go in that direction like that. We can simplify this because this electric field strength is opposite to this electric field strength. That will cancel out, the equal and opposite. This electric field strength is equal and opposite to that electric field strength. They will cancel out. So the resultant electric field strength is actually 2 times magnitude of the electric field strength we calculated in part 1. So our answer is 2 times K. I'm going to write this down here just now, and I'll explain where that comes from in a minute. 3.2 times 10 to the minus 6, of course, represents the fact that it's a microcoulomb, and 0.15 squared is distance A squared. That's going to give us an answer of 2.6 times 10 to the 6 newtons per coulomb. That is the units of electric field strength. So let's remember them. It says the magnitude of Q is there. Determine the magnitude, we've done that, and the direction. So we have to say the direction is towards the bottom right charge. And that's good enough for describing the direction. Now, why did I say K is 8.99 times 10 to the 9 and just leave it at that? Well, K is actually equal to 1 over 4 pi epsilon naught. And epsilon naught is a permittivity of free space. 4 pi is just a number. The permittivity of free space is given as 8.85 times 10 to the minus 12. And there's loads of units in here. It's like, let me see if I can remember. C squared n to the minus 1 meters to the minus 2. That is what the permittivity of free space is. And it's how easily fields can travel through free space in its simplest form. If we pop all those numbers in, then what we get is 8.99 times 10 to the 9. So instead of writing this whole equation with 1 over 4 pi epsilon naught on it, we just use the constant K, and it's easier for us to remember that K is equal to 8.99 times 10 to the 9. Question 2. 3 fixed charges plus Q, and minus 2Q are at the vertices of an equilateral triangle. What is the resultant force on an electron at the centre of the triangle? We've said it's equilateral. That means we know that the distances between the electron and all the charges is the same. Great, we can start off with that. Now what we're going to do is we're going to use a ruler, and we're going to draw a representation vector arrow showing the electric field strength felt by the electron due to each of these 3 charges. We'll start with this positive Q here. The electron is negative, this is a positive charge, so the electron will be attracted towards that charge. And we're going to give this vector arrow a representation line of 2 centimetres towards that charge. Great, now let's go to minus 2Q. This electron is going to be repelled by this minus 2Q. So the electron is going to feel an electric field strength repelling away in that direction. It's going to feel 2 times the length of the arrow before. But because it's vectors, we're going to add it tip to tail. So 1, 2, 4. That's what the electric field strength felt by the minus 2Q added tip to tail to the original one. Finally, we're going to look at this one. The electron is going to be repelled from there. It's going to be repelled in that direction. And it's going to be repelled by the original length. The magnitude is going to be half of that one that we've just done. Great. Now what we want to do is find the resultant vector. We go from the electron to the end of the final arrow, and we draw an arrow like this. So the resultant field strength felt by the electron is in that direction, which gives us an answer of B. A minus 5 microcoulomb charge and a plus 10 microcoulomb charge are a fixed distance apart. Where can the electric field be 0? Let's look at each charge and consider the electric field due to each of those charges. We'll go with the 10 microcoulombs first. A positive test charge would be repelled from this 10 microcoulombs. Let's draw the field lines representing for that. So I'm going to go along to 1, 2, 3, 4 centimetres across, and it's going to be felt that way. Given that we're only looking in one direction, there's going to be an electric field strength in that direction too. And I've just used 4 centimetres as just a representation. The 5 microcoulomb charge is also kind of electric field. We'll draw that in red. It's going to be smaller in magnitude, and it's going to be in the opposite direction because a positive test charge is going to be attracted towards that 5 microcoulombs. It's going to look like that. Let's look at position 1. If we were to place a positive test charge there, it would feel an average force, let's just use the word average force, in that direction. And it would feel a very weak force, very, very weak force in that direction, because we're still feeling the effects of this electric field strength. It's just very weak. Let's go to position 2. We'd feel quite a strong force in that direction, and it would also feel a strong force in that direction too. Finally, in position 3, it would feel a weak force in that direction and a weak force in that direction. The position where it's most likely to average out to 0 or add to 0 is position 3. This would be very strong in that direction, and this would be probably stronger in that direction. So I'm going to say it's C, position 3 only. 2 point charges are at rest as shown. At which position is the electric field strength the greatest? We're going to do this again. We're going to take our ruler and draw a representation of what the electric field strength due to each charge would be. Plus 5 microcoulombs means that a positive test charge would be repelled, and it would be repelled, let's just say it's 6 units across. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So that's a representation of the electric field strength due to the plus 5 coulombs. Let's look at the representation of the field strength due to the minus 2.5 coulombs. It would be attracted, and it would be half the amount that we gave to the plus 5 coulombs. It would be like this. Let's consider each point A, B, C and D and consider the effect of the electric field strength due to each charge. At point A, it's going to feel force in that direction from the 5 microcoulombs, and it's going to feel a very weak force in that direction due to the minus 2.5 coulombs. At B, it's going to feel quite a strong force in that direction due to the plus 5 coulombs, and it's also going to feel a strong force in that direction due to the minus 2.5 coulombs. So this is a contender so far. Let's look at D. D is going to feel a very weak force in that direction due to the plus 5 coulombs, and it's going to feel a strong force in that direction due to the minus 2.5 coulombs. Finally, at C, it's going to feel a weak force in that direction due to the plus 5 coulombs, and it's going to feel a relatively strong force in that direction due to the minus 2.5 coulombs. If we add them together, it looks alright, but I reckon our biggest, strongest point is here. So our answer for question 7 is B. Here we have another question very similar. The diagram shows 2 equal and opposite charges that are fixed in place. At which points is a net electric field directed to the right? If we go to minus Q, positive test charge is going to be attracted towards it, so the electric field strength is going to be in that direction. And for the plus Q, a positive test charge is going to be repelled, and it'll have the same magnitude as the other one because it's the same size of charge. For each x, y and z, let's now look where we expect the resultant force to be. For x, we're expecting a large force in that direction, per test charge due to the electric field, and a weak one in that direction due to the positive charge. So is this electric field strength directed to the right? Yes. Why? I'm going to look at a very weak electric field strength in that direction and a much stronger electric field strength in that direction. So yes, that is net right as well. So I'm looking at C.
The diagram shows magnetic field surrounding two current-carrying metal wires P and Q. The wires are parallel to each other and at right angles to the plane of the page. What is the direction of the electron flow in P and the direction of the electron flow in Q? So for this, we're going to use the right-hand screw rule. Right-hand screw rule, and the thumb, I'm going to try and draw this here. The thumb goes in the direction of conventional current, which is positive to negative, and the fingers curl around in the direction of the field lines. That's supposed to be a hand and these are supposed to be fingers, and that's the wrist. Okay? So if we're looking at this right-hand screw rule and we have the conventional current going into the page like that, into the page, then we point your thumb in that direction into the page and your fingers will curl round in that direction. If we have your thumb pointing out of the page like this, if you take your thumb and point out of the page with your right hand, your fingers will curl in that direction. Right, let's take that. And remember, this is conventional current. What I'd like you to do is look at P. We want the fingers to curl anti-clockwise. So is your thumb going to be pointing into the page or out of the page? You do it for me now. My thumb, personally, is pointing out of the page. So P is out of the page for conventional current. But we're not looking at conventional current. We're looking at direction of electron flow, which is opposite to conventional current. So even though our thumb is pointing out of the page, the direction of electron flow is into the page, so we've got to have either A or B. Let's look at Q. Which direction of your thumb pointing into the page or out of the page will cause the magnetic field lines to be clockwise? Well, it's into the page. So at this point, we're going to point our thumb into the page, which is a conventional current. So the electric flow current is opposite to that, which is out of the page. And the answer is B. A non-uniform electric field with field lines as shown exists in a region where there is no gravitational field. We're only dealing with electric field. X is a point in the electric field. The field lines and X lie in the plane of the paper. A. Outline what is meant by electric field strength. It is the force per unit positive test charge. That's enough. That's all we need to write. B. An electron is placed at X and released from rest. Draw on the diagram the direction of the force acting on the electron due to the field. Okay, well, we know that the field lines go in the direction that a positive test charge would take. That tells us that this is a positive side and that is a negative side. If we're suggesting that X is an electron, that makes it negative, it's going to be attracted towards the positive and repelled from the negative. So the electron is going to feel a force to the left in that direction. C. The electron is replaced by a proton which is also released from rest at X. Compare, without calculation, the motion of the electron with the motion of the proton after release. You may assume that no frictional forces act on the electron or the proton. So the first thing I'm going to say is when you're asked to describe the motion, you want to use one of four terms. You want to use constant velocity, you want to use stationary, acceleration, or deceleration. And in this case, we're obviously going to look at acceleration. It's not going to stay constant because it's experiencing a force. The other thing that stands out about this question is the idea of compare it with the electron and the proton. And I'd like to really have a look at quickly, before I write anything down, what the differences between an electron and a proton are. Well, an electron is a negative charge and a proton is a positive charge. A proton is heavier, it's got a greater mass, And an electron has a small mass because the mass of an electron is 9.11 times 10 to the minus 31, which is tiny. And the mass of a proton, I don't know if I can remember this, is 1.67 times 10 to the minus 27 kilograms. I think that's all we need to know. Okay, so we've compared the electron and proton. We know we've got to use the word acceleration, and we've got to get 4 marks. So the first difference in the motion will be the electron will accelerate to the left. We have the force on the electron above that's going to the left. The proton will accelerate to the right. Another difference, A equals F over M. The charge on each electron is the same, and the charge on the proton is the same. And the force, when we're looking at electric fields, is E equals F over Q. So F equals EQ. So the force felt by the electron and by the proton is the same. However, the mass is greater for a proton. The magnitude of acceleration for the electron will be greater than on the proton because the force is the same, but the proton has a greater mass. For the force mark, we have to look back. The electron is moving towards the left, and you can see that the field lines are getting further apart. That means that the electric field strength is lessening at this point. The proton is moving to the right, and you can see that electric field lines are getting closer together. That means the electric field strength is increasing. So they're not going to accelerate constantly. The electron is going to experience a smaller magnitude of acceleration as it moves to the left. The proton is going to experience a larger magnitude of acceleration as it moves to the right because F equals EQ, and as this increases, then the force on the proton increases. So let's go back to number 4. Both particles will increase in speed. However, the electron will experience a lower magnitude of acceleration as it moves away. My writing is dreadful. From X. Conversely, proton has increased acceleration due to electric field getting stronger. I'm so sorry about my writing here. The diagram shows some of the electric field lines for 2 fixed charged particles X and Y. X must be a positive charge because all the field lines are moving away from it, and Y must be a negative charge because the field lines are moving towards it. The magnitude of the charge on X is Q, and that on Y is small q. The distance between X and Y is 0.6 metres. Draw that in. And the distance between P and Y is 0.82 metres. I know it's the 3 significant figures, I just can't be bothered with that. At P, the electric field is 0. Determine to one significant figure the ratio Q over Q. If the electric field is 0 at P, that means the electric field due to X is equal and opposite to the electric field due to Y. So EX equals EY. We're going to use the equation for the radial field strength, which is KQ over R squared. So EX is equal to KQ, X is Q, okay, over the distance from X to point P is 0.6 plus 0.82 all squared. And the electric field strength equation for Y is going to be K small q over 0.82 all squared. Cancel out the K's and let's cross multiply. So we've got Q 0.82 squared equals small q 0.6 plus 0.82 all squared. Now we want to bring it down to the ratio of Q over Q, and that means the answer will be 0.6 plus 0.82 all squared over 0.82 squared gives us an answer of 2.998. We wanted to one significant figure. The answer is 3. An electron is placed at a distance of 0.4 metres from a fixed point charge of -6 millicoulombs. A. Show that the electric field strength due to the point charge at the position of the electron is 3.4 times 10 to the 8 newtons per coulomb. Okay, well, E equals KQ over R squared. You'll remember from question 1, we're saying that K is equal to 8.99 times 10 to the 9. Q is the charge on the fixed charge, which is 6 times 10 to the minus 3. You'll notice I haven't put minus in there. We're really just looking at the magnitude of it, so we don't need to put the direction in. And R squared is 0.4 squared. Let's plug all of that into our calculator, and that gives 3.37 times 10 to the 8 newtons per coulomb. We're going to give everything to two significant figures, so 3.4 times 10 to the 8 newtons per coulomb, which is what the question asked. B1. Calculate the magnitude of the initial acceleration of the electron. A equals F over M, and F, remember here, E is equal to F over Q, so F is equal to EQ. So instead of putting F up here, we'll put EQ over M. The electric field is 3.4 times 10 to the 8. Charge on the electron is 1.6 times 10 to the minus 19. The mass of an electron is 9.11 times 10 to the minus 31. Find that from the data booklet. And that gives us an answer of 5.97 times 10 to the 19 meters per second squared. I think that's a bit too many significant figures, so we're going to do 6.0 times 10 to the 19 meters per second squared. B2, describe the subsequent motion of the electron. Do you remember earlier I said when it described the motion, you're looking at using one of those 4 phrases. In this case, again, we're going to use acceleration. But we've got to give it 3 marks. We're going to say it's accelerate. We're going to say that it's going to accelerate to the right because it's going to be repelled from the charge. The acceleration is going to decrease because the force is going to decrease as it moves away from that charge. So the magnitude of acceleration decreases, but the speed still increases. It's still increasing its speed, it's just not increasing as much because the magnitude of the acceleration decreases. You can put that into sentences if you want, but it'll accelerate to the right. The magnitude of the acceleration will decrease as it moves away from the charge, but the speed will continue to increase. There's your answer.